So we have learned about Lebesgue-dominated convergence theorem, which allowed you to consider sequences of functions like these, okay, and again they would converge to some function pointwise f of x, and you want to know whether you can apply integration on both sides. You have that the limit of the sequence of integrals converges to the integral of the limit of the sequence. Okay, so now we're going to do something completely related. Actually, we're going to use that result to extend it to something called parameter-dependent integrals. What do we mean here? We must have a function that depends on two variables first. So no more sequence. Actually, we're going to have one function that depends on two variables, x and t, and we will want to perform integration. But so let me integration, but with respect to only one of the variables. All right, so let's make it with respect to t. And the idea is that, well, now, instead of considering a sequence depending on discrete index n, I'm going to consider the function that depends also on the continuous variable x, okay? But which is not, again, the variable of integration. The x here appears nowhere in the integral. Well, I mean, it's not the dt, it's not related to the dt. So that means in terms of integration, it acts just like a constant, just like previously the n in terms of integration was transparent. Okay, it was just when we go to the limit that we had a problem. So it's going to be the same idea. What's happening if I want the x to go to some specific value x0? Do we have that this integral is converging to the integral of f at point x0 t dt? So it's still a question of exchanging integration and limit. This time I want to know if the limit as x tends to x0 of my integral depending on x and t dt is equal to the integral of the limit as x tends to x0 of f of xt dt. So it's again, it's completely related to our previous case, except that now instead of a discrete index n, we just have a continuous variable x. Okay, so we're going to have two theorems. One theorem that concerns continuity, which looks like exactly what we've just done. Continuity of a function f just means that when the variable tends to some value x0, then it's equal to some, it's continuously, we have that the limit is well defined to f of x0. Okay, so we're going to have one theorem on continuity and another theorem on differentiability. And of course, again, you understand that it's really a question of limit, because differentiability is just, okay, the derivative or the partial derivative, because as our function f depends on two variables, it has partial derivatives. The partial derivative is again just a limit, the limit of the growth rate. Okay, so let's dig a bit closer into the hypothesis we need, and maybe let's begin with some example to illustrate a bit more this problem. Okay, so some example to illustrate the kind of problems we may have. Let's consider this function that is going to be defined by some integrals. An integral, let's make it between 0 and plus infinity, of e of negative t divided by t plus x dt. So here you notice that the integration is with respect to the variable t, so x acts like just a constant in terms of integration, but still, however, the result is going to be something that depends on x. So let's say that this is how I'm going to define some function f of x. let's even make it f1 of x. Okay, so you notice also that the interval of integration is infinite, so we are in a case of improper integral, and we still have to study the differentiability, the boundedness of this integral. Okay, so let's consider different cases. If x is strictly greater than 0, all right. So what's happening if x is strictly greater than 0? Do you have a problem in 0 for t is equal to 0? Do we have an integration problem in a neighborhood of 0? Well, the answer is no. Why? Because it's just simply going to be well defined on the top, because e of 0 is 1, and at the bottom I'm going to have t is equal to 0 plus x, which is strictly greater than 0. So no, we don't have any problems, as the function, the inner function, is well defined for t is equal to 0. Now, okay, do we have a problem at infinity? Well, always, as it is infinite, we still have to study that. So, in a neighborhood of plus infinity. Okay, so I remind you that we're studying this for the variable t, because it's the variable of integration. So what do we have? What is our function? We could maybe give that a name. Let's say that this function, well, can be seen as f depending on x and t, right? In neighborhood of infinity, we have well, our function f of x and t is equal to e of negative t over t plus x. Okay, so choose any strictly positive value of x. What would you say about the function e of negative t divided by t plus, let's say, 3, right, in terms of integration at infinity? Well, there's no problem, because you know that it's going to be, well, after some point at least, it's going to be smaller or equal to 1 over e of t, for instance, and this is a well-bounded integral function, so we can go further. So, well, we have this in terms of absolute value, it's going to be smaller, so you know we can use integral sign then on positive functions. So if I integrate with respect to t this part, it's going to be smaller than the integral with respect to t of that part. So that's on all plus, that's on all plus. And of course, if you remember, this is bounded. Well, you can even calculate that. It's just going to be 1 if you integrate that up to 0. Okay, so in plus infinity, we don't have any problem. It's also going to be bounded. Now, what's happening for x is equal to 0? X is equal to 0. What is the function I have now to integrate? I've got the integral between 0 and plus infinity of 1 over t e of t dt. Okay, so in neighborhood of plus infinity, no problem. No problem. For the same reason as above, it's just going to be bounded above by 1 over e of t, all right, so which is integrable. But in the neighborhood of 0, well, we do have a problem. We do have a problem because the function is simply going to be equivalent to, so 1 over t e of t is going to be equivalent in the neighborhood of 0 to 1 over t, because e of t is just around 1, equivalent to 1. It's going to be equivalent to 1 over e of t. And if you remember, again, your theorems on improper integral, then the integral have the corresponding integrals have the same nature. e of t dt, same nature as the integral 1 over t. Okay, which you know, of course, that it's diverging whether you consider it in neighborhood of 0 or in neighborhood of infinity. Okay, so that could be seen as a strange result. Why? Simply because, well, if you consider the initial function, the small f of xt, it seemed, well, perfectly well-defined continuous. Okay, yeah, we still have a problem in 0, but it didn't seem that complicated. You could try, and so what we can say is that this function is well-defined and continuous on R plus star. Okay. Another interesting example. Okay, let's make this new function. Let's define a new function by the integral between 0 and plus infinity of x e of minus xt dt. Okay, and so let's say that this is going to be my f2 of x. Again, it's a function of x because I do the integration with respect to the. And well, the previous case, you could say, well, that's going to be as a function of two variables. The previous case, in terms of x and t, we already saw that there would be a problem when both t and x would be equal to 0. This function here is, well, the nicest you could imagine. I mean, it seems absolutely continuous and it's well defined and so on. Okay, so let's have a look at this integral. The good thing in that case is that it's going to be, you can perform the integration here. So the primitive of this function with respect to t is simply minus e of minus x t. Okay, excellent. So what does that mean? When you are doing the integration at plus infinity to 0 minus the value in 0, so that's going to be e of 0 is 1, so that's plus 1. Okay, so for all x, it seems to be working well, except that what do I have? If I put f2 of 0, okay, what's happening? I have the integral between 0 and plus infinity of 0 times e of 0 times t dt. And what is that function? That's a well-defined function. That's 1. That's 0 times 1. So that's the integral of between 0 and plus infinity of the 0 function, which is 0. So you see, even a simple example like this seems to be problematic because we couldn't foresee any problems. Although if you just perform the integration if you perform the integration without the specific value of 0, you get a constant value of 1, and if you plug 0, well, you get 0. So we have not non-continuity, obviously, in 0. So we feel that there must be something going on, and we need more hypothesis. Well, we need a good theorem in order to tell us when this kind of function that we define is going to be continuous or not.